So this is the second online lecture for ECE 341 random processes. Last time we talked about derived random variables for continuous random variable case. Today we will make some brief comments about conditional probability models for continuous random variables, really just a logical extension of what we've seen before. And then we'll move into what is chapter 5 in the textbook, where we're going to start talking about pairs or multiple random variables. So very quickly, let's talk a little bit about conditional. So we'll look at this idea of a conditional probability, or what you might think of as a conditional probability model. So conditional probability for continuous random variables. We'd seen conditional probabilities for discrete random variables. Really, the only difference here is in notation. Instead of having probability mass functions, we will have probability density functions. So we can look at a probability density function f of some random variable x conditioned on some event, call it a. So f of x given b, I think I said a there, but b, let's let it be of some variable x then. And really what we get on this is we just get the non-conditioned probability density function fx of x divided by the probability of b. And you get that when x is an element of that event b, and you get 0 otherwise. This fits in our model that we had talked about before, that when you condition on some event, you get rid of what couldn't happen. That's the 0 otherwise. So whatever didn't happen, you just get rid of the probability associated with that. For those things that did happen, x being part of b, you go ahead and keep the original model. You just scale it in such a way that the overall integration of the resulting distribution, the conditional distribution, remains to be 1. This, of course, does have a real simple requirement. It does require that the probability of b be greater than 0. Otherwise, if it couldn't happen, it wouldn't make much sense to do it anyway. And if you had had it equal to 0, you would have gotten an undefined divide by 0 in there. Let's do a very, very simple example on this. So I'm going to go ahead and take a look at a uniform random variable. If I had a uniform random variable from 0 to 1, so that's going to have height 1. This could be some fx of x, right? We've seen this uniform model before. If I wanted to go ahead and create an event b, b is the event that b indicates, let's say, indicates, it's the event that x was greater than 1/3, something like that. Then we could go ahead and take a look at a conditional model, f of x given b of little x. And what is that going to be equal to? Well, it's going to be like our probability density function, fx of x, which is just 1, right? That is just going to be 1. So I would have my fx of x, which we know to be 1, divided by probability of b. That's as long as x is greater than 1/3, right? But it also means that x has to be less than 1. That was from the original distribution. So we're going to be looking at whether this x is between 1/3 and 1. And it will be 0 otherwise. If we go ahead and start plugging in the different things, we do need to know what the probability of b is in order to carry this out. Probability of b, right, is equal to the probability that x is greater than 1/3. Simple calculation in this case, it's an integral 1/3 to 1 of my probability density function fx of x dx, which is equal to, in this case, 1/3 to 1 of 1 dx. That's just going to give us 2/3. We could have probably done that without the integration. All right, so now we can put things back together. I know that my conditional probability density function fx of b, f of x given b of x is equal to then my non-conditional probability density, which is 1. Probability of b was equal to 2/3. 1 divided by 2/3 is going to be 3/2. So we get 3/2 there for 1/3 less than x less than 1, and it's going to be 0 otherwise. If I go ahead and draw that out, not too hard to do, right? We know in this particular case I'm going to go out by thirds, something like this. So I have a 1/3, 2/3, 3/3 is just 1. These are values of x. I'm trying to look at f of x given b. as a function of x. And we had something coming up 1, 2, and here would be my 1.5 or 3/2, something like that. And starting around, right, 1/3, we're going to hold that value until we get to 1. So we can go ahead and finish this thing out. It's 0 before 1/3, it's 0 after 1, and I have a value of 1.5. Okay, so let's just quickly take a couple looks at this guy. It is a probability density function as we'd expect. It's non-negative everywhere. So we do see in this particular case, if we are doing our mental checks, f of x given b of x, we do see it is greater than or equal to 0. That makes us happy. And then we see that the integral of this, right, conditional probability density should be equal to 1. Can we verify that out? Well, sure. This is a rectangle. We know what the area of a rectangle is. That area of the rectangle there, right? That area of the rectangle is equal to, in this case, the height, 1.5 times the width, that's 2/3. So that's 3/2 times 2/3 equals 1. So we do indeed see that this thing maintains all the necessary conditions for a valid probability density function. It was just conditioned. Now, if we go back and look at the original, right, original definition, and then also this this result that we got, what did we end up doing here? We had an original distribution, f of x, right? There it is. F of x was just this uniform. But we had an event b that said that you went from 1/3 greater. So we knew that the world that we were living in had to be sitting out over here. So that's the stuff we kept. And then we ended up getting rid of, right, everything before that. So we got rid of those pieces. If we didn't do any scaling on this, we would have a function that went from 1/3 to 1 that would have height 1, which would not integrate to 1. It would not give us a total probability of 100%, and it would not be a valid probability model. So what do? We scale this whole stuff up, right? We move it up. That's the divide by probability B, so that we can get something that overall has just area equal to 1. When we take a conditional probability, the underlying distribution shape doesn't change. We just get rid of things, right? Or keep things and then scale everything so that the overall area is equal to 1. So very similar to what we saw for discrete time, and really no surprises there. Conditional probabilities also have all the properties that you would expect any valid probability density function to have. So for example, we can do things like expectation. We can take the expected value. We can take it of just x or any function of x. So let's go ahead and say, what is the expected value of a function g of random variable x given b, for example? So this is a conditional expectation. If I wanted to do that, we know that this is going to be an integral because it is a continuous random variable. Go ahead and go over all time or all values of the possible random variable, and we would have that function g of x just weighting what? Well, it just weights that conditional distribution, fx given b of x. And then we would integrate out the variable x. This is a center of mass calculation using the weighting function g of x, expected gx. You just put gx into the integral, and because it's a conditional expectation, you use the conditional probability density function. Really, I don't think we have to do much more there. I would say go ahead and read the book examples. Read the book examples. They're good. I think the book does a nice job of giving some nice insight into these things, and really has some nicely done examples. What we're going to do now is we're going to switch over. We're going to move into a kind of a different concept. We're going to be looking at extending what we've learned already about random variables, and we would like to extend it to multiple random variables at once. So next, I guess we could say it is, next, let's consider multiple random variables, right, all at once. Turns out that this is a bit of a complication to what we've learned already. We're going to need to have some consideration of some other interactions that occur. And it's a little tricky to do this if you're just going to jump up to n random variables all at once. So for right now, let's just restrict ourselves to the smallest case that involves more than one random variable. So we're going to look at pairs of random variables. So let's start easy. Let's start easy with just two random variables. So two random variables is more than one, as we would expect. And we need to be able to handle both of them. Now you could sit there and say, well, maybe I just handle the one and then I handle the other. And certainly you can do that, and there's nothing wrong with doing that. But handling one of the random variables by itself and handling the other random variable by itself is an incomplete way of dealing with multiple random variables, because random variables can have interactions between them, and those interactions can be really, really important. So let's start. We will start with some experiment. So we're going to start with an experiment. We're going to start with an experiment that generates two random variables, right? So we're going to do some experiment, and the outcomes of those experiments are going to generate two random variables, and we're going to call one of those guys X, and the other one we're going to call Y. We could call it anything, but for just ease, let's call them X and Y. To describe, I need to get that spelled right, to describe X and Y along with their dependencies, and that's the kicker, along with their dependencies. We'll consider what are called joint CDFs, and then connected to that are what are called joint, well, we're going to need either a probability density function if it's continuous, a probability mass function if it's discrete. So we're going to have two random variables. We do some experiment that gets us those two random variables. We need some way of describing them. We've already seen in previous chapters that we describe the nature of a random variable using their distribution functions, either the probability density / mass, or the accumulation of probability density or mass, which is the CDF. We're just going to do that in 2 dimensions. So we are going to come up with a joint CDF and a joint probability density or probability mass function. Let's start out with the joint CDF. So we'll look at the joint CDF first. The joint CDF. The joint CDF will try to use a notation that we've seen before, cap F. It's a function of two random variables, so I'm going to subscript it x comma y. So it's the CDF of the pair of random variables x and y, and it does have to be a function of two observation values, right? The one for x and then the one for y. This is describing a probability, and it's kind of like what you'd expect. It's the probability that my random variable x is less than or equal to little x, and it is also at the same time simultaneously the probability that y is less than or equal to some little y. I can draw this out in the xy plane, and I think it will give us some insight as well. So let's go ahead and let the horizontal axis be my x variable, right? My x random variable. The vertical axis be my y random variable. We're taking a particular value of x, right? And we're taking a particular value of y. So I could locate that point, right? The point little x, little y in the two-dimensional random variable plane, xy plane, cap xy plane, and we get that point. The CDF, the joint CDF, says we're looking at the combined condition that x is less than little x and y is less than little y. So I'm going to go ahead and draw that in a color here. So for x to be less than little x, it's going to be going this way. And for y to be less than or equal to little y, we need to be able to take that guy and go down. So I can do that, and I'm going to just sketch it in here. I can do that just by really getting this section, this quarter part of the plane, something along those lines. So if we could somehow represent probability in the xy plane, right, we're going to be adding up all the probabilities or integrating up all the probabilities over a quarter plane, where the vertex of that quarter plane is going to be at the point xy, something along those lines. So you can already probably get an idea of where this is going. We're going to need to do not just single sums, we're going to have to do double nested sums, or we're going to have to do double nested integrals, something along those lines. A few things that we can note about this joint probability density relationship through the CDF, this joint CDF, is the following. So we can note a few things. The first thing that we'll note is that the CDF of X, just using it by itself, this is the probability, right, that X is less than or equal to little x, something along those lines. And what do we know that that's equal to? Well, we can get that from the joint distribution as being the probability that X is less than or equal to little x, and that y is less than infinity. Probability that y is less than infinity is always going to happen, so that means we aren't really taking y at all. But this notation really gets us in terms of that CDF, that joint CDF. So we could do this as fxy of x comma infinity. So there's a part in the xy plane, right, that I can look on that joint CDF to find just CDF values. So the CDF of x is built into, the information is contained in this joint CDF. We can do, of course, the same thing for y. So I could say fy of y is equal to cap fxy of infinity comma y. So we know that the CDF of x and y each, the information of it is contained in this joint probability model, this joint CDF. Some other things that we might be able to get on this, a CDF is just like any old CDF. We know that the CDF itself has to be greater than or equal to 0. So I could say fxy of little xy has to be greater than or equal to 0. And it also has to be less than or equal to 1. You can't have any negative accumulation of probability, and you can't accumulate more than 100%. Some other ones that we might do in here as well is we might notice that fxy of minus infinity comma y is equal to fxy of x comma minus infinity. So if I've gotten nowhere in either x or y, that means I couldn't have accumulated anything. That's going to have an accumulation of 0. The last one I would do in here, so none of this is really too surprising. Basically, if we take a look at this second one I just did, it says that we have to start out at 0. If you go all the way to the left or you go all the way down, right, the start of x or the start of y, you have to start at an accumulation of 0 probability. That's always been the case for our CDF. This last one is going to tell us how it increases. CDFs we know to be non-decreasing functions, so we could do that and condition something like this. If x is less than or equal to some value x1 and y is less than or equal to some value y2, right, then the CDF, right, for x comma y has to always be less than or equal to the CDF of x1 comma y1, which means as you increase either x or y, right, the CDF can't get smaller. It can only stay the same or get bigger. It's a non-decreasing function. So really this whole thing tells us that fxy is a non-decreasing, right? It's a non-decreasing function. This should make you all happy because this is exactly the kinds of behaviors that we'd seen for CDFs before. Basically, all we've done is say, even though this is a CDF that's a function of two variables, it has all the properties we know and love about CDFs. Has to start at 0, has to end at 1, right? And it has to do so in a non-decreasing way. It's just a function of two variables now. So if I was going to plot this thing, I'd probably need some sort of surface plot, which gets a little more tricky. I do think that that's a point worth just kind of highlighting at this point right now. It can be tricky. It can be tricky. It can be tricky to use these joint CDFs. And I think what we find out then is that the joint probability mass functions or the joint probability density functions are generally easier. And so for the most part, we're going to probably spend most of our time looking at these joint probability mass functions or these joint probability density functions, which of course are connected. They have equivalent information to the joint CDFs. They just tend to be a little bit easier to manipulate, a little easier to work with. So let's start with the discrete case. We're jumping back. This chapter talking about multiple random variables is going to include both continuous and discrete. We'll start out with discrete just like we did for the univariate random variable cases. We started discrete before we did continuous. So let's go ahead and look at this thing called the joint probability mass function. So PMF is just the same as we had before. It's just our abbreviation for that discrete random variables kind of probability model. We can do this just like we did in discrete. We can call a P. Now, instead of just one random variable, it's going to be a function of two, pxy. I could put a comma between there. I don't. It's just implied. So this is not P of x times y. It's just P of the random variables x and y. We know it's a function of two guys in here, x and y. And this is equal to not the probability of an accumulated amount of values. It's the probability that x equals little x and that y equals little y, just exactly like we would expect. You could also look associated with it. There could be some range space. We could call that S of xy. It is the set of values, coordinate pairs, if you will, x and y, such that the probability of xy of little xy, right, is greater than 0. So a range space tells us those values that can occur, right, that have probabilities greater than 0. It's kind of the way we decide what values of x and y are important to consider, or that we maybe need to take a look at. And then we just define what those probabilities are. I would look at this whole thing, and I would say that we could often represent in various ways. It depends a little bit on how we got it, what kind of underlying distribution is. It could be in various ways. It could be things like an equation of two variables, right? It could be a list, just a list of coordinate pairs. You could do things with some sort of a matrix, right? You could do things with some sort of a graph, all sorts of possibilities for describing or otherwise showing these joint probability mass functions. When we have this joint probability mass, or when we're talking this consideration of two random variables, I also think that we need to be able to talk what we mean by an event. So I think this is somewhere in the book. It's one of the theorems. We're not going to worry too much about the specific theorem, but let's think about an event B and getting its probability. If I want to know the likelihood of some event B, right, we're going to have to do what? We're going to have to sum up all the events or all the pieces of our experiment that are part of B. So we're going to sum up over all coordinate pairs x and y that make up or an element of B. And what do we need to do? We have to add up their individual probabilities, which we know we get from this joint probability mass function, pxy of little xy, right? So if we're trying to find the probability of some event B, we're going to just be adding up a bunch of points in the xy plane that are those that make up B, and just add up their corresponding probability mass values. So as an example of this, I think you could think of a really simple case, right? We could have something like x equals roll a four-sided die, something like that, and y equals flip a coin, and we're going to do that heads equals, we're going to call that heads equals 1, tails equals 0, something like that. And so if I looked in the x, y plane, let's let them be independent. So x and y independent of one another. So the outcome of the roll doesn't depend on the outcome of the flip. We know x could have 1, 2, 3, 4 values. So we could have 1, 2, 3, 4. And y could be a value 0 or it could be a value 1. If I was going to be describing the range space, right? The range space is going to be the values that either x or y, or their combination, that the values of x and y, these pairs can occupy. There's 8 points in here. X can be 1, 2, 3, or 4, and for each one of those values, 1, 2, 3, or 4, y can be 0 or 1, something along those lines. So this is a graphical depiction, right? So I've given a graphical depiction, a graphical depiction of this range space for my random variables x, y. Now I could do something like this. I could have the event B such that, right, we could sit there and say that the coin flip x, right, something along those lines, is equal to y plus 1, something like that. I don't know why I came up with this, but we're just looking at when are those cases that what I rolled by my coin, it's equal to y plus 1. Well, we could start looking at possible values of this. If x is 1, right, y can either be 0 or 1. If I put 0 in there, I would get 1 equals 1. So that would certainly hold to it. So I'm going to go ahead and circle that one. When x was 1 and y was 0, right, we could get that, that 1 equals 1 condition satisfied. If I put x equals 1 and y equals 1, then I would get 1 equals 1 plus 1. That's not true. So that wouldn't be a point in that space. So for the value of x equaling 1, there's only one value of y that satisfies that. If I move to x equals 2, right, y equaling 0 doesn't satisfy it because I would get 2 equals 1, but y equaling 1 does satisfy it, right? So if x equals 2 and y equals 1, 2 equals 1 plus 1, so that's this other point sitting out here, that also satisfies it. And it turns out there's none others. So this set B really includes 2 points, right? It includes 2 points. And if I wanted something like the probability of B, right, then I would need to, as the equation had said, sum over all those points in x and y that make up B and look at their corresponding probabilities. So I would need in here pxy of x being 1 and y being 0, and I would need to add into that pxy of, well, what do we need? X equaling 2 and y equaling 1. And that would be it in this particular case. You know, in this particular case, since everything's equally likely and there's only 8 points, those are each an eighth. So I would get a 1/8 here plus a 1/8, and that would give us a total probability of a fourth. And that sort of makes sense if you go back to the piece that we have over here. I'm highlighting in green, whereas B, right? We get 2 out of 8 points being included in B, and so we would expect the probability, since they're all equally likely, to be 2/8 or 1/4. Okay. So let's go ahead and move to some additional examples, maybe some ones that are a little bit more involved. So as another example, let's do the following. Let's go ahead and roll. We're going to roll 2 six-sided die. And then we're going to consider the sum of these guys. So we're going to look at some event. Let's call that event A. That event A is going to be the sum of x plus y being equal to 7. So I don't know, for those of you who've been around the Fargo-Moorhead area for a while, you know we have a cab company in town called the Lucky 7 Limo. So if you want to think about this, they have the Lucky 7 limo service, and it shows 2 six-sided die, six-sided die, in this particular case, six-sided die. And I guess their idea of a lucky event is that when you roll those 2 die, they sum to 7. So we're going to try to play with this a little bit. Before we get too much into thinking about the distribution of this guy or how we describe it, let's think of a game. Suppose that you were going to roll 2 die and we were going to look at the sum of the 2 die coming out. And so event A, right, is that sum, x plus y. And we wanted to look at a couple possible outcomes of that. We might be interested in that event A, right, being equal to 7. How possible or how likely is event A? A little hard to know, right? At least just from an initial statement. We do need to do a little bit of calculations. I'm going to throw in here a second example before we get to the full multiple models here, so that we can continue this comparison. So we had roll 2 six-sided die and consider the event A as being the sum being equal to 7. Let's call that example 1, right? And then I'm going to look at example 2 as being a slight variation of this. I'm going to roll fair 6-sided die, call that guy X, and then I'm going to roll a fair X-sided die, which we will call Y. So if I rolled a 4 on my X, then I would roll a 4-sided die. But if I rolled a 2 on my X, I'd roll a 2-sided die. So that second die roll absolutely seems to depend on that first die roll X. Now I'm going to come up with a sort of equivalent event. Let's look at an event B as being the sum of those guys, X plus Y, and also let those guys be 7, so a lucky 7 as well. And we could sit there and say something like, well, how likely is event B? So what's the chance that B occurs, that I get a lucky 7 in this alternate die rolling experiment? To make it even a little bit more rich, let's try this. If I let you pick either the first example or the second example, so you can roll 2 fair die, or in the other case, you could roll 1 fair die and then follow that with a die that depends on the first roll. You have event A or B, they both are indicating that the sum is equal to 7. And I tell you something like this. If I pay $1 for event A, and I pay $1.50, right, for event B, which game do you choose to play? So let's just summarize what this means. You got 2 games, 1 or 2. The first game involves rolling two fair die, and if their sum is equal to 7, I pay you $1. The second game involves you rolling a first die, and then you roll a second die that depended on the outcome of that first die. And if the sum of those 2 guys comes out to be 7, I give you $1.50. Which game do you play? Maybe not 100% obvious at this point. And again, I think this will justify or at least emphasize this need for doing calculations. Here's how I think we should try to understand this. I think we should get some explicit understanding of these two experiments, if you will, and understand how the probabilities are accumulated or how they're there, and think about these events A and B and how likely they are. And then once we know how likely they are, we would know what their expected payoff is, and we should be able to come up to a good solution. If we just looked at it from a somewhat naive standpoint, you might sit there and say, well, I'm sort of interested in this idea of doing B, right? Because B has a higher payoff. It's $1.50 instead of $1. Well, if B is less likely than A, you would be less likely to get that $1.50. So maybe it's not as good of a deal as it seems on first blush. So let's go back to example 1 again, and we're just going to see if we can get a way of understanding how this experiment rolls out. I'm going to go ahead and draw it just like we've done in the past, but because we've got 2 variables coming on in there, we have X and Y, right? We know X can be 1, 2, 3, 4, 5, 6, and Y can be the same sort of things, 1, 2, 3, 4, 5, 6, and we're going to get just a representation here of the intersection of all these different outcomes, all these pairs of outcomes that could be associated with this first experiment. So X could be 1, 2, or right now I'm on X equaling 3. And for any value that we roll of X, the same outcome values are possible for Y. So every dot that I'm showing here is just one of the outcome possibilities in our experiment space. You could call this the range space, that Sx sub Y. S sub xy, something along those lines. So we had 1 through 6 in x, and we have 1 through 6 in y, and what we see in there is that there's 36 outcomes, right? There's 36 outcomes possible. We do know that we had this event A, which was x plus y being equal to 7, right? So our event A was x plus y equaling 7. If, for example, we had x equaling 1, there's only one value added to 1 that gives us 7, and that's y equaling 6. So I know that's in there. For x equaling 2, y needs to be 5, and for 3 it's 4, and for 4 it's 3, and for 5 it's 2, and for 6 it's 1, something along those lines. So in this particular case, event A, I could designate in the xy plane, right, as this diagonal grouping of outcomes. 6 out of those 36 points ends up having this chance of getting outcome A. So if I was going to be trying to come up with a little bit more formal models here, or at least descriptions, I could say something like this. I could say that whoops, got the wrong variable there. I could say that the joint probability mass function, Pxy, right, Pxy of little xy is equal to, well, we know that there's 36 things possible. Each one's equally likely, so we're going to have a 1/36th chance, right? And this is for x comma y, an element of the range space xy, right? And that it's 0 otherwise, something along those lines. Probability of A in this particular case, right, is equal to a sum over all xy points that are an element of A, which is x plus y equaling 7. And we know there's 6 values of those. And in each one of those, we add up what is the probability mass function, the joint probability mass function, which is 1/36th. So I end up getting 6 points each of weight 1/36th. That gives me 6/36 or 1/6. So probability of A in this case is 1/6. I don't know who named Lucky the lucky limo, but it's not horribly lucky, right? It's only 1/6 chance in there. So we've got probability of A being 1/6. If I wanted to think then, what's the potential amount of money that I could expect, right? What is the expected payoff for this exercise 1 with this outcome A, right? You could ask something along those lines. Well, I know the probability of A is 1/6, and I know that every time we pay out A, we get $1. So the expected payout for this guy should be 1/6 times $1, right? Which ends up giving me, well, that's 0.166 going on forever dollars, 16 2/3 cents. So a little more than 16 cents is what I'd expect to get returned on playing this particular game. Now we're going to go ahead and look at that example 2 again. We would like to be able to get a description or a graphic of this one as well. I'm going to do that in this particular case by doing an XY plot. We had talked that there's lots of different ways of describing these guys. I think XY plots are fine in this case. So I'm going to look at my X on the horizontal, my Y on the vertical. X is the first one. It's a fair die, so I'm going to get 1, 2, 3, 4, 5, 6. So I have a 1, 2, all the way up through 6 on there. Each one of those is equally likely, right? Now, Y is an X-sided die. So if I roll a 1, then that means Y is a one-sided die. If I roll a 1, there's only one possibility I can get. If X was a 1, Y has to be a 1. Now, there was a 1/6 probability that I got X, right? For any one of those values, 1 through 6. So the value X equaling 1 has a probability equal to 1/6. And there's only one value of Y to share that 1/6 with. So I think that point right there along column 1 is going to have a 1/6 probability. I could have done that above, I guess. So that guy's going to have a 1/6. So let's go ahead and keep that there. Now, as I move into X equaling 2, when I roll X equaling 2, now Y is going to be an X-sided, or in this case, X equaling 2-sided, a 2-sided die. So Y could be 1 or 2, and so I get 1 or 2 in here. Well, X only had a 1/6 chance. That 1/6 has to get shared among 2 different values. So Y was supposed to be a fair die. It's just a fair X-sided die. So I know each one of these is going to be a 1/12, right? Because 1/12 plus 1/12 gives me 1/6. So I had 1/6 total probability to share between these 2 points. It has to be shared equally, so I'm going to get a 1/12. And hopefully you start seeing the pattern here. For 3, I get 3 possible values of y. For 4, I'm going to get 4 possible values of y because it's a 4-sided die. For 5, I'm going to get 5 possible values because it's a 5-sided die in y. And for 6, it's going to be 6 possibilities in there. In the case of 3, right, I had 1/6 that has to get shared 3 ways. There's only one way to do that. That's with 1/18 if they were all fair. The next one in there is going to be 1/24. The next one in there is going to be 1/30. And the last one's going to be 1/36, something along those lines. So what we have here is sort of an interesting situation. You can definitely see that x and y depend on one another because the region of support here is not rectangular. This one's triangular. So there are values of x. Larger values of x mean more possible values of y, right? Smaller values of x mean fewer choices of y. Clearly, they're dependent because we don't have kind of a rectangular looking region of support. Furthermore, the points themselves, these things that can happen in here, aren't all equally likely, right? The different values of x are each equally likely, but the different points in the xy, the pairs, are not equally likely. If you roll an x equaling 1, you know y has to be 1. That has a chance of 1/6 of the time. When you go through this experiment, 1/6 of the time, you're going to get x equal 1, y equaling 1. But if you go to something like x equaling 6 and y equaling 1, there's only a 1/36th chance of that happening. So the probabilities definitely change in there. We could come up with whatever kind of mechanism we wanted to write that out. I think I'm not going to write an expression or a list. I think that the way I've done this graphically is adequate for this current example. We were more interested in this event B, and so if you remember, B was supposed to be such that x plus y equals 7. And again, I'm going to try to think of that. It's the same places in the xy plane that we had seen before. So if you put in x equaling 1, the only value of y that would give us a sum equaling 7 would be 6, but that's not part of the range of support. So there's no value x equaling 1 that still finds us in this event B. Same thing with 2, same thing with 3. When we get to 4, however, I can have x equaling 4, right, and y would be equaling 2. Did I get this right? Let's see, 1, 2, 3, 4, 5, 6. Let's make sure that we are getting this guy in there. So 4 and 3, yep. So if I'm at 4, then y is equal to 3. So 4 plus 3 is equal to 7. And if I go to x equaling 5, y equals 2. It's the same things that we'd seen before. And if x equals 6, I get y equaling 1. So I still have that event, the sum equaling 7, going on that diagonal, right? It's just now that the range of support only has 3 points on that diagonal. As a result, if I was going to come in here and find the probability of B, right, that is going to be equal to a sum of 3 points, right? So I'm going to be summing up this idea of x being equal to 3 and y being equal to 4. Nope. X equaling 4 and y equaling 3, x equaling 5, y equaling 2, and x equaling 6 and y equaling 1. Something along those lines. What are those individual probabilities? We can get it right off the graph. So there was a 1/24th chance that x was 4 and y was 3. And there was a 1/30th chance that x was 5 and y was 2. And there is a 1/36th chance that x was 6 and y was equal to 1. So if I do the math on that, I'm not going to go through all of that. You end up getting 37 over 360, which is 0.1028, something like that. Just a hair over 10%. Let's go back then to how much money, what is the expected, we had looked at before. We said, what's the expected payoff, right? What was this expected payoff for this first experiment where the sum was equal to 7 when the payoff was $1? Since we only expected to get paid a sixth of the time, the expected payoff was 16 cents, a little over 16 cents. If we come down here and we say, what is the expected payoff, right? What's the expected payoff of this second example for that same thing with that event B, which is just that the dice sum up to be equaling to 7. We know that the likelihood, right? The likelihood of getting paid was 0.1028, and the amount we were getting paid was $1.50. So you just multiply those guys together, and we end up getting 0.1542. So it's a little over 15 cents that we would get in this second experiment. So now we can make a more informed decision. It turns out when we go back here way at the start, when we were looking at these guys, we had the first experiment paying $1, right? The second experiment paying $1.50. From a real simple comparison of the payoffs, one might be inclined to do B. It seems like it's a much better deal. It's 50% more than the payoff for A. But when we go through and we think about what we expect if we ran these experiments over and over and over again, you're going to come out just a little bit higher ahead on this first one, right? Your expected amount returned is 16 2/3 cents, and for the second one, it's 15.42 cents that you would expect payoff. So you definitely would want to play the first game in this particular case in order to come out ahead. Not that you're likely to come out hugely ahead on any of these. We have just a couple more things that we want to do, and then we'll call it a lecture. In this particular case, I want to also think about something called the marginal probability mass function. That marginal probability mass function is a way of getting a probability mass function univariate from a joint distribution. So just language-wise, we can talk about this idea of a marginal. So what is called a marginal probability mass function. So a marginal probability mass function is something like fx of x and py of y. Boy, I'm not doing very well. We need to make this, since we're talking the probability mass function, so let's use our notation px of x and py of y. So our marginal probability mass functions are just the univariate PMFs. We want to get these guys, the marginal PMFs, we want to get them from our joint distribution pxy of xy. So when you think about what it means to marginalize, right? Marginalize means to kind of isolate something from others. And so if I marginalize x, right, we're going to get rid of all the dependence on y. We're going to get rid of all the information about y. We're just going to be looking at x. So the marginal PMF px of x doesn't have anything about y in it. It's just getting us back to that univariate case. It's like we only were looking at the x variable, or we were only looking at the y variable. Turns out this is not terribly difficult to do. If we have the joint distribution, it's easy to get. You can again see this from a theorem in the book reading if you like. So px of x is equal to what? It's a sum over all values y that are part of their range space of pxy of xy. So I just sum out the y variable for each value of x, okay? This really is like our previous. It's like our previous calculation of experiments with an event, if you will, here, x equaling x. So we're just taking an event being, let's have a particular value of x. So let's go back to one of the examples we had before. We'll do this just very, very quickly. If we rolled our two fair die, right? So we had a 1, 2, 3, 4, 5, 6. So we had 1 through 6 as being my x. And I had a 1, 2, 3, 4, 5, 6, 1 through 6 of being y. Let's look actually at the second experiment. So the second experiment had not 36 values, but substantially fewer, right? Because that second die roll did depend on x, something like this. So we got a range space something like this. So this was example 2 from before. From this, we knew that we had things like, well, there was the 1/6 there, and then we had the 1/12, and the 1/18, and the 1/24, and the 1/30 column, and the 1/36 column, something along those lines. And this whole thing described our pxy of xy. It was our joint distribution. The dots show us the range space, right? And those values above the columns tell us the individual probabilities, those joint probability mass function values for each one of those points. If I want the marginal px of x, and what was x? X in the experiment was roll a six-sided die. You already know what the model of that should be, right? It should be 1/6 for each of the 6 values. So I want to get Px of x from these different values that are in the joint probability. So I can do that individually for each one if you wanted. So for x equaling 1, for example, I'm going to get 1/6 because there was only one point, right, that summed down to give us 1/6. I just drop all of these points, all of these probabilities down onto the x-axis because I want to get rid of all the parts of y. So if I just look at that, there was only one point to drop down. The second one is going to be 1/12 plus 1/12, so 1/12 plus 1/12. Well, that's equal to 1/6. That's no problem. That's x equaling 2. The next one's going to be what? 1/18 plus 1/18. There's 3 points, right? And we're trying to get rid of all the values of y that occurred, right? So all 3 of these values, right, we're adding them all up just to give me what's the likelihood of x. Going back up here, right, you just sum over all the values of y possible holding that value of x. So I need to sum across all these values of y holding x equaling to 3, something along those lines. 1/18 added 3 times over equals a sixth, and we can keep doing that, and what we find out is exactly what we expected. Px of x is equal to what? It's 1/6, right, for 1, 2, all the way up to 6 for x equaling all those values, and it's 0 otherwise, something along those lines. What's interesting in this case is that we can do something completely different. We could also find in this case py of y, the marginal distribution of y. This is much harder to visualize just because of the sequential nature of how we describe the experiment. But as far as doing it from our graph, very easy. We're just collapsing all the points down, not onto the horizontal axis, but onto the vertical axis. So let's look at py and y, and let's not do the whole thing. Let's look for little y equaling, how about 3, something like that. So I'm going to look at, in this particular case, this whole probability mass function for y equaling 3. What is it equal to? Well, if I come up here, and I'm going to do this in just a little bit different color, if I come up and I think about where y is equal to 3, so here's y equaling 3. I need to get rid of all the x dependence, right? So I need to sum across all those different points in there. So there's going to be an x equaling 3, 4, 5, and 6. There's 4 values in there. It starts out at a value of 1/18, right? And so I'm going to come in here and I'm going to get a 1/18, right? Plus a 1/24th, plus a 1/30th, plus a 1/36th. I'll let you do the math on that, but you can see that we definitely get some value. It's not a real pretty value. And every value of y, just looking at y by itself, is going to be something different. It's not going to be uniform like x was. Okay, one more example, and then we'll be done in the lecture for today, I think. So let's try this as an example. Let's let there be a product, okay, a product that has both an electrical component and a mechanical component. So a product has both an electrical and a mechanical components. I'm going to let x be my electrical part, and I'm going to let it be binary. I'm going to let that be 0 if the part is bad. So whatever went into the manufacturing didn't work, and 1, it's going to be good. I'm going to do something similar for the mechanical. I'll just let y designate the functionality of the mechanical part of the component of this product. And I'm going to let it be 0 if things went badly mechanically, and 1 if they were fine mechanically. So we can think of this as being, does it pass mustard or not? Does the electrical part, the microprocessor or whatever on it work? And does the mechanical part work? I can look then at a joint probability model, Pxy of xy. There's not many choices here. You can have both electrical and mechanical succeed, right? You can have both electrical and mechanical fail, and then you could have one succeed and one fail, two different cases of that, where it's either the mechanical or the electrical that fails. So there's a total of 4 binary. There's 2 binary things. 2 to the 2 is 4. There's 4 choices here. So in this particular case, doing some sort of list of probabilities, I think is totally fine. I can look at different values of x and y. So they could have both failed, for example. The electrical could have failed, mechanical could have succeeded. The electrical could have succeeded, mechanical failed, or they both of them could have succeeded. And we could have done, there's really nothing else in here. So we've completely described it. Let's let them both fail with probability. So I can look over here as to the probability of this, right? I'm going to let them both fail with probability 5%, something along those lines. I'm going to let mechanical succeed and electrical fail with 5%. I'm going to go ahead and let electrical succeed and mechanical fail with 20%. And then I'm going to let everything else happen with the balance. So we had 30% above, so I'm going to need 70% to take care of the rest, something along those lines. We could have also done this, right, with some sort of a probability table. These are things that we've seen before as well. So I could have looked at having the mechanical part and the electrical part fail, pass, something like that. And we could have gotten something here where both failing was 0.05, right? Electrical failing and then mechanical passing 0.05. And then we had the other one here is being 0.2 and 0.7, something along those lines. So if I was interested in, oh, and I guess I could also, if you wanted to, do this in a graph form, right? I could have done this x and y, and I could have looked at 0 and a value 1, and this guy could have been a 0 and a value 1, and that gives me four points in there as well. And you could label those guys. I'm not going to do that here in this particular case. I'm interested in this particular case in having, right, what is the marginal distribution, F, Px of x. So what's the probability model for whether the electrical part is working or not? We need to sum out everything to do with y. So for example, if I just look at this probability table, right, I'm going to be getting rid of all the different stuff that could happen with y and summing them out. So 5%, for example, is 10%. 10% of the time, I do get failure in the electrical, right? And in the same way, I can sum up when all the different values of y for when electrical succeeds. And so that's going to be 90% for when electrical succeeds. Could have gotten the same thing in either of the other representations as well. So I just sum up over the values y, and I find my px of x in this particular case, right, is going to be 0.1 for x equaling 0. It's 0.9 for x equaling 1. You could do a 0 otherwise in here. In the same sort of way, I could have found a py of y, something along those lines. If you go ahead and add up in the y sense, something along these lines, the idea that the mechanical fails, maybe it was a harder mechanical problem, 25% of the time we get failure of the mechanical, 75% of the time we get success of the mechanical. There's no other options, something along those lines. Could have done that in red, right? We're going to get failure of the mechanical, either 20 and 5% for the two different x values. So that's a total of 25. Same thing, or same idea for y, equaling 1. It's success. Okay, so we got marginal distributions of these two. I have a marginal distribution. The electricals work at 90% of the time. I've got a marginal distribution for the mechanical, 75%. One of the things we'll notice is that even though this particular example has stuff fitting on a rectangular kind of region of support, these guys do have some interaction. They do have some dependency, right? These are not all equally likely points going on in here, and they certainly are not independent, right? And so we've got some other kind of complications going on in here. If they were independent, we would just multiply their individual probabilities. That would mean that pxy equaling 0, 0, right? Both things failing would be 10% times 25%, which would be 2.5%. It's double that, it's 5%. So we know something else is going on in here, and this joint probability model, this joint probability mass function model helps us capture that set of dependence that's going on in there. We're going to speak more on this, but I think it's good enough now just to make a final observation for this lecture. We will say generally, the marginals, right? The marginals aren't enough to describe the joint distribution with all of the dependencies, with all dependencies that could occur. So we can get marginal distributions from the joint, but we cannot get the joint distribution just solely from the marginal distribution information. There would be many, many joint distributions that would have the same marginals. We need to know something about those dependencies. It's part of the reason that we truly do want something like a joint distribution instead of just individual models for the individual variables. Individual models are fine for understanding that individual variable, but it doesn't tell us what's going on in interaction between them. Okay, I think that's enough for today. We'll do another one soon.